it is they're not always the best, you know, in terms of that. So yeah, they'll be there. So you'll learn about probability first, and then we'll continue to move on from probability. We'll work into some statistical stuff. Right at first, it'll be just some basics, like for instance, mean, median, standard deviation. If you don't know what standard deviation is, buckle up. You're going to get very, very, very familiar with standard deviation. And then from there, we're going to continue on our list, and we're going to get into some distributions. And so distributions are the idea that everything in life, pretty much everything we see around us, follows a certain distribution. So here's a perfect example of this. When you, I don't know, let's say you go to the grocery store tonight, and there's some 7'6" guy checking out groceries today. He's your checker out guy. Like you do a double take, maybe 3 or 4 double takes, because that's not something you see every day. That's just a little weird. It would probably be worthy of going home. You'll never guess who I saw at Fred Meyer's. Oh, you know, no one ever starts off the conversation. You'll never guess what I saw today, honey. And then you're like, okay, tell me. Yeah, I was like walking on the street today, and I saw this guy. He was like 5'11". And no, that's it. No, because no one says that. Because why? Because the average male in the United States is 5'10", 5'11". Okay, that's the average height. It's right in that ballpark. No one even blinks an eye about that. And we know, for instance, that heights, weights, IQs, etc., 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 are distributed what we call using a normal distribution. Normal because, well, you know, they're normal. Whee! Some people would say it's the bell curve. Yeah, it is. That's the idea of it. And yeah, and if you may have seen this in the past, but between a certain value here and a certain value here, there's like 68% of the population that lie between there and there. And go out further, it's 95%. And if you've had stats 243 or 361, you've seen some of that before. And so the idea of this is, you know, which things would follow the normal distribution, and what can we glean just knowing the fact that it came from a normal distribution. Other things don't come from that distribution. We'll look at some that are called the binomial distribution. And the binomial distribution is the idea that it's an either or situation. There's one or the other, okay, hence the binomial. And it's the idea that you're going to play a certain number of times, whether it's having children or whatever it happens to be. But let's just say you're going to have 6 children. Good for you. And what's the probability to have, you know, 2 girls and 2 not girls, or 4 not girls? Okay, well, I don't know. So you can figure that out. It's an either or situation. Cool. You could do win or lose situations, make a basket, miss a basket, whichever it is. And based on how you set the problem up, it might be a binomial situation. Other times we might see the Poisson distribution or the exponential distribution. All these other distributions that'll come about based on what we're seeing. And then so based on the fact that you know it's going to come from a normal or a binomial or whatever distribution, then it saves me a ton of work. Because if I know it came from that kind of a distribution, I automatically know what the standard deviation is. I automatically know what the mean is. I automatically know a ton of stuff about this based on what kind of distribution it came from, okay? And so that is a beautiful thing. We spend quite a bit of time studying these different distributions so that we can identify them, okay? In the real world, in your generic real world scenarios, there aren't too many out there that you'll run into that have not been identified anymore. Just because they pretty much have all been identified. Hey, when this and this and this happens, oh, that's a geometric distribution or whatever it happens to be. So we will spend quite a bit of time talking about that. But again, the reason we talk about them is twofold. First of all, based on which distribution it is, we'll know a ton about it based on what distribution it is. And so you need to understand what distribution it happens to be. You need to be able to recognize them. So we'll do quite a bit with that, okay? Once we understand what the distributions are, then we'll do some pretty cool things. So we'll learn about a little thing called expected value. You already understand this intuitively in your head. Expected value. If you were to play the lottery tonight, okay, go down and buy you a Powerball ticket, what do you expect to win? Well, no one expects to win. But are you going to lose $1 every time you play the game? If it's $1 ticket, I know what it costs. Let's say it's $1 ticket. And you're like, well, if I played long enough, if I played every week $1 a ticket, if I played long enough, theoretically, yes, I should probably win one time or two in there. Okay, that's right. So in other words, what is the expected value is also another way of saying what's the long-term average of your winnings. Okay, if you were to play this game in theory forever, what would you expect to win per play? And so that's the idea of, for instance, if you work for an insurance company, and I only talk about life insurance in this class, because you need to take a whole, like, you can major in, oh, come on, Jay. Come on, I'm trying to tip my tongue. You can major in actuarial studies, and then you can have all kinds of fun conversations about all the other kind. But just term life insurance, because you're dead or alive. Either you don't die, and thank you for paying us for 10 years for the premium, and you lose because you didn't die, so you didn't get the $100,000 from the life insurance policy. If you die, well, then you win the $100,000. Unfortunately, you're dead. So, but it's the idea that, and so over time, the average consumer is going to lose, quote unquote, money every year, and the insurance company is going to make money every year, because that's how they make money. Is they agree to pay you in case you die or get in a car wreck or whatever it is, and they agree to pay you, but you pay them all the way along. You're paying a little bit because you have a very small chance of dying. Okay, if you're in your 20s, perfectly healthy person, you don't jump out of airplanes or jump motorcycles or anything else like this. You're just a normal 28-year-old person, you know, whatever, just normal job, whatever. You are going to have a very low chance of dying, and so because you have a very low chance of dying, then I, as the insurance company, am not going to charge you much to play. However, if you had a very high chance of dying, I'm going to have to charge you a fortune, because I'm most likely going to have to pay out on you. Okay, and so that's what expected value is from our daily lives scenario. One other place where that kind of shows up, totally shows up, is in Las Vegas. I'm going to use my big computer for this. When you go to Vegas, everybody knows that when you play, you're going to lose. That's kind of how the whole game is played. That's how they make money. And so what I'm going to do is just simulate some data here real quick. So one of my favorite games, although I've never actually played it, the idea of it makes me happy, is roulette. I like how the rules go, and I like how the math is very very pleasurable to me to think about. So I'm going to pull this up here real quick. So you may not know it, but there's 38 spaces on a roulette wheel. Okay, 18 of them are red, 18 are black, 2 are green. There's a 0 and a double 0. They're both the green ones. There's odds and evens. I don't remember, the odds are black and the evens are red. It doesn't matter. That's the game. So let's say that you go to Las Vegas and you're going to bet on evens. Okay, you're going to bet on evens. Well, turns out there are 18 out of 38, so you will win. And then your probability is 18 out of 38. And you will lose 20 out of 38. Oops. And if you're playing along at home, you're like, wait, doesn't that sound like there's just either or, Jay? That's right. It's just either or. And so if you win, turns out you're going to win $2 for a $1 bet. And if you lose, obviously you're not going to win anything. Okay. So what I'm going to do is I'm going to simulate you playing this game. Let's do, I don't know, 10,000 rolls, shall we? That sounds fun. And so in essence, what we're telling the computer is, hey, listen, basically roll a 2-sided dice, if you will, and roll it, I don't know, 10,000 times. Cool. So think about this. If I'm going to do this, I'm going to bet 10,000 times on a roulette wheel. It costs me $10,000 to do that. Yes. So in a minute, when I win or lose or whatever happens here in just a jiffy, I'm going to, oops, don't put your wine in. What's going to end up happening is I'm going to end up winning in just a minute. I'm going to sum up column A here. There they are. Okay. if I take the sum of A1 to A10,000, you will see that I made $9,400, almost $9,500. That is amazing. You're like, whoa, that's exciting, Jay. Not so fast, Haas, because to make $9,500, you had to spend $10,000. Oh, crap, I lost $504. That's right, you sure did. But how much is that per game? It's a good question. So if you average it out per game, you would see that you lost basically a nickel every time you played the game, okay? Now, here's the cool thing, and this is why they do this kind of games in Vegas, is they don't want to bleed you dry. They don't want you to lose 12 bucks every time you play. If I lose a nickel every time I play, I'm like, yeah, whatever. Because listen, I won $2. Oh, look, I won 2. Oh, I lost. Oh, look, I lost. I won 2. Oh, yeah, I feel good about myself. Cool. Other people go, listen, I'm going to go to Vegas. I'm going to go big. Okay, cool. I am going to bet on a single number. I'm just going to bet a single number. So let's say, what do you want? That's 17. I'm going to bet on 17, by God. All right. So if I'm going to bet on 17, there's a 1 in 38 chance of winning. Okay. And then, of course, you're going to lose 37 out of 38 times. Okay. If you win, you get, let me see, I do the math in my head. Pardon me while I do the math. Come on, Jay, you got this. Come on, you got it, buddy. 18, 17. You win 17 plus your bet. No, come on, is that right? No, you win. No, there it is, baby. You got it now. I got you. You're going to win $35 plus your bet. So you're going to win $36, and you're going to win nothing, obviously. Okay. And so if you do this data analysis routine again, and let's see, let's change this to this instead. And let's put our output in B1 this time for a good time. Boop. And look at you lucky sucker. Look at that. You should only won 1 out of 36, but look at that. Right off the bat, you won already. And you're like, oh, but then I lost a lot. Dude, when you're hot, you're hot. When you're not, you're not. Wow, that's terrible. But then you win bam, bam in a row, right? Okay, so let's just add up column B here. Now, so equals the sum B1 to B 10,000. Look at you won $8,900. Okay, but again, you spent 10,000 to win that, so it wasn't a real good play on your part. And so, and you'll notice that this time, in fact, it comes out you lost 10 cents every time you played. Okay. In fact, the actual theoretical value is actually that you lose a nickel no matter what bet you do in Vegas. No matter what bet you make, you will always lose a nickel every time you play. That's what it comes out to. And you're like, well, Jay, you just simulated it. I know, I simulated it 10,000 times. You'd think that'd be enough, but it really isn't enough. It was enough for the basically 50-50 odds evens routine. But for the 1 out of 38 chance, not quite enough sometimes. I've done it in class before where I had a whole bunch of people in the classroom and some people would end up winning money, for God's sakes. And you're like, I have no explanation for that. However, when you then take all 20 or 30 people in the room and average their winnings, somebody over here ended up winning money. Like they ended up winning $25 or $30 or whatever it was in the end. Somebody over here lost $7,000, something stupid. When you average them all together, it actually comes out right around a nickel every time you play. Now, why do I care about those expected values? Well, expected values are what we base our decisions on, okay? This is the most likely outcome to happen. So based on what we know is most likely to happen, okay, now what are we gonna do, okay? And so expected value is a big, big topic, and we'll spend quite a bit of time discussing it, okay? Just a couple more things I wanted to mention before we run out of time here. And that is, another one to talk about is expected value and then standard deviation. And standard deviation is just basically a measure, deviation is a measure of how spread out the data is. And it's a relative term, it's a relative measurement. And what I mean by that is this: if you're looking at heights of people. It might be about 2 inches ish is the standard deviation for heights in the United States for adult males. That's pretty close. But the number 2, obviously in inches in this case, but if you had, let's say, the price of homes in Portland, the standard deviation is going to be in the like $30,000 or $40,000 standard deviations. Why is that? Because house prices vary greatly from one end to the other. So because the average is so much bigger, standard deviation is going to end up being bigger just because of that. It would be weird if most of the houses in Portland were within like, $12 of each other. That would be kind of crazy. Okay. So clearly it's a relative measurement. The bigger the average is, the bigger the standard deviation is going to be just in general. That's very similar to a taller person is typically going to weigh more than a shorter person, typically speaking. Okay. Now, I know my son is a beanpole, and that's how it goes. But in general, taller people weigh more because they're just bigger. It's the same idea. If you have a bigger average, you're going to end up with a bigger standard deviation most of the time, okay, almost exclusively. And we'll talk more about how to get there. But again, these will be known either based on a distribution or we can find them using integrals and sums. Integrals in the case of what we're going to call a continuous distribution. So the normal distribution, for instance, is a continuous distribution. Any number between wherever and wherever, between like 3 feet tall and 8 feet tall, pretty much any height between here and here is acceptable height for an adult in the United States, I guess, right? Not very likely, really, really, really likely in here. Find someone who's 5'6". I'll tell you they're not 5'6" if I had a better tape measure. Okay, so we can always get a better tape measure. And so the idea is that it's not just distinct chunks across there. You're on a continuum, if you will. Okay, versus things like how many hot dogs did you sell today? Well, it's a whole number. It's 1, 2, 3, 4, 5, and so on. How many girls do you have? We have 5 girls. Okay, cool. Well, that's a number. That's a discrete distribution, and they only come in discrete packages. Okay, and so in the case of a discrete distribution, we'll use summations. In the case of a continuous distribution, we'll use intervals to find it. Okay, and then winding down toward the end of the term, okay, we'll get into what's called joint distributions. And so this is kind of how it's going to build all the way through. So up here, the number of kids, number of girls in a 4-kid family, that'll be a binomial distribution. Okay, it's a very obvious distribution, but it's just one thing. It's the number of girls. Okay, down here, the joint distribution. So the idea will be that Z is in essence a function of X and Y. And I don't really want to write Z, I want to write probability. So the probability is a function of some X and some Y. Okay. Now, wait, so what are we going to do with these? Well, we're going to do a variety of things, but one thing we're going to end up doing is double integrals. And when we integrate this thing, dx dy or dy dx from wherever to wherever and wherever to wherever, better equal 100%. Okay, nothing new about that. And you may recall in Calc 4, we did some problems where we said y was between 0 and 2x or something, and then we said that x went from 0 to 2 or something. I don't know, maybe something like that. In this case, I'm going to write this up here first and then tell me what you think. Okay, I'm going to have to flip my dx's and dy's around, yes? Well, why is that? Well, because y clearly depends on x. In other words, x is in its limits of integration. Okay, that makes, in this case, then y and x are dependent on one another, or in this case, y is dependent on x. I could, of course, draw this picture. Why I did that exactly? I'm not going to do that. Hang on. I could draw this, and so x equals 2 is here, and then y equals 2x is here. So we're looking at this triangle here, yes? That's what we're integrating over. So I could turn this inside out and solve it differently. So I could say that y goes from 0 to 4. And then I could say that I could turn this inside out. And if I wanted to write this equation, which is y equals 2x, in terms of x, it'd be x is equal to y over 2, correct? So x would go from y over 2, that's the minimum that x can be, over to a maximum of 2. And again, I could integrate the other way. But the point is they depend on one another, okay? If it was an integral situation like this, where I went from 1 to 3 and 2 to 4, clearly they both go, it's just we're integrating over a box. In this situation here, we would say that these guys are independent, okay? Now, it's possible that this is not an independent situation every time, and we'll talk more about that when we get there. Things like this that would occur to this is it could be a situation where it could be it's a man's age and his wife's age. All right, cool. They might be very well independent of one another. They're probably not independent of one another. Most guys don't just type in, and I think I feel confident saying this, Match.com, find me a woman with a pulse. No. Typically, you specify an age range, okay? What's that age range based around? Your age range, okay? So it's dependent situation there. The one depends on the other, and it could be just the opposite way around. The girl's looking for a guy that's somewhere around her age, or maybe way older. Who knows? It doesn't matter. But the idea is they're not independent always. Sometimes they are independent, and we'll talk about what does that mean for these things. If it's independent, the x can do whatever it wants to do, the y can do whatever it wants to do. But again, if this is the interval, the x can go only from 1 to 3 and 2 to 4, and this thing will integrate to 1 every time. Okay, and we'll talk about these. We can talk about from these guys here, we could find what is the expected value of y. We could do all kinds of cool things based on these guys. Okay, and then again, as we get here, where are these functions coming from? It's a good question. Sometimes this distribution right here, and by the way, these distributions will all, of course, be continuous. Sometimes we know how x is distributed, we know how y is distributed, and we know they're independent. Okay, so I need an x and a y, hence we'll multiply them because they're independent. Sometimes they're a dependent relationship, and someone smarter than us has come up with an equation that says this tends to describe what we're seeing. Cool. And what can we do based on that? Okay. Again, the whole point of probability and statistics, and mostly statistics when we need to talk about, the whole point of this is we need to be able to make decisions. Okay. That's really the bottom line. Anybody that sits around just talking about statistics just annoys me to no end. Love baseball, love statistics. It's the only thing in the world when you mix the two of them, it gets worse as far as I'm concerned, okay? Usually you take two good things, put them together, it's a better thing. And that makes it gross for me. I love talking about statistics in terms of what can we do to solve a problem with statistics, okay? Not muddy the waters with them, but actually solve a problem with statistics. So clearly, if you're going to do that, you need to be able to rely on the data. You cannot have just crappy data. You cannot have be slipshod when you're recording your data, okay? I don't want to be spending millions of dollars to fix a problem that doesn't really exist, in other words, okay? I don't need to buy whole new equipment because somebody's done a bad job of capturing data. We had a principal or a superintendent some years ago. I used to be in charge of testing in the math department at the high school. And I remember this one kid, he passed the state math test and he was so excited. And he jumped up and ran out of the classroom. And I went over there and son of a gun, he did pass. And I couldn't believe he did because he was not very smart. But he made such a scene out of it, like really made an indelible mark on me that he passed. And so then there was a couple other kids that were similar to that. And I was keeping notes of who passed and who didn't in my spreadsheet. And so then at the end of at the start of the next school year, they sent me the district's report, and it wasn't right because this kid passed. I know this kid passed. I know this kid passed. And so we were looking through it, and I said, this isn't right. So she sent me another spreadsheet, which was different than the first one. I'm like, well, for crying out loud. So I complained again. I got a third spreadsheet that was different from those ones as well. And so I got in this big discussion. And finally, the superintendent goes, just use the damn data, Jay. And I said, I would love to. You tell me which one to use. And then she said, just pick one. It doesn't matter. And I went, oh, for crying out loud. So at that point, it's like, why waste my time doing any kind of study? Why waste my time looking any further into it? if you're not going to be giving me good data to make a decision on, I'm not interested in what you have to say at that point. Okay. And so that to me is kind of where that to me is what this is all about, is I need the probability in order to make a decision on statistics. I think, again, this class is probably a little more probability heavy in terms of some of the double integrals later on in the chapters. It would have been cool to have some other things in here, but whatever, life goes on. And so that's kind of where we're going. My hope is that the Wednesday night lessons will be a lot more how comes and how can I apply this and that sort of thing, again, for an hour. And then the videos will talk about all the real things you need to learn. Again, I kind of glossed over a few things tonight. For instance, with factorials, I go into a lot more in depth in the videos, so just watch those as well. Fridays, I'm going to be doing a office hours, probably somewhere around noonish. I'll make a decision tomorrow for sure. What I'm going to ask that you do is email me if you plan on coming. I sat alone a lot looking at an empty computer screen last term, and I have better things to do. So I will send out the exact times, I think, tomorrow. But if you want to be there, just send me a note. Hey, I'm going to be there, so I know to look for you. If I've sat there for half an hour and no one has showed up and no one told me they were going to show up, I'm just going to get off and go away. There'll be a link to that. And every Tuesday, I will send you a link for Wednesday's class. Last term, I tried to recycle the links, and I had a couple of issues with it. So it's just easier to make a new link every time. And I'll just email that out. Okay. So as soon as class is over, I'm going to go back in and I'm going to tweak some of the dates. I'm going to fix those 2 mistakes on the syllabus as far as my phone number and the time. And I'm going to link to that that book online, and so you can see it. The book is this guy here. I'll pull up a picture of it if you want. Boom, 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 boom. Probability and statistics, engineers, Walpole. There he is. That guy right there. This one. There he is. Well, that guy. Yep, that one right there. Yep. And I believe the ISBN is in the syllabus. So that's the one. I remember that picture being that weird, but that's basically what the book looks like. All righty. Any questions? Things you don't remember?
Only a reminder. Can we start the class at 5:30?
Is everyone all right starting at 5:30?
Yeah, it's fine.
Works for me.
Yeah, it doesn't matter.
All right. I'll do 5:30 then. I'll just send out a reminder next week. We'll do 5:30 to 6:30 instead.
Oh, thank you so much.
Yep. No problem.
Good day.
All right, you too. Bye, Al.
Thanks, Jay.